Great. Hello, everyone. Very excited to welcome everyone back to week 4 of the Computational Fabrication Seminar, Season 2. I'll be the chair for today's session, which is about fabrication of items with embedded functionality. As usual, we'll first have the motivational talk and then the deep dive talk, and we'll do the Q&A for both at the end. Now, it is my great pleasure to announce the first speaker, Alexandra Ion. Alex is an assistant professor at the Human-Computer Interaction Institute at Carnegie Mellon University's School of Computer Science, where she directs the Interactive Structures Lab. Her research and expertise lie at the intersection of human-computer interaction, computational fabrication, and material engineering. Her work has been published in and awarded by premier venues such as ACM West and CHI, and she's been invited for exhibitions, including a permanent exhibition at the Ars Electronica Center in Austria. Alexandra, please, the floor is yours.
Well, thank you so much. Thanks so much for the introduction. I'm just gonna share my screen and arrange some windows, sorry. Okay, there we go. All right, yeah, thank you so much for the invitation. This is very core, this seminar series is very core to what I do, which is obviously then a good fit. As Amy already was so kind to introduce, I lead the Interactive Structures Lab at CMU here. So I wanted to give you a little bit of background. So I did my PhD in HCI, which is still kind of my core area of focus and where I publish. And then I kind of wanted to really embrace this interdisciplinary field of work that I'm in, and did my postdoc with Olga in computer graphics. So now I'm an assistant professor at CMU, and I am always looking for enthusiastic students and postdocs at all levels to work with me. So if you're interested in the things that we do in the lab, feel free to reach out at any time. So I think, as you know, many of us here in the computational fabrication seminar area, we are aware that 3D printing is so interesting and intriguing because it is really the first and only technology to enable, almost arbitrary geometrical complexity in what we can, make in terms of physical artifacts. So that really inspired like a whole field that allows us to create materials with engineered properties. So here I wanted to show a few examples. The one on the very left shows this lattice structure that is not 3D printed in this case, but it really has this geometric complexity to it that enables it to be very, very lightweight and yet strong. And you see how lightweight it is that it can actually sit on this standalone. Another material with engineered properties is this ring in the center that by its internal structure redirects sound to be noise canceling, yet allow air to pass through, which is very fascinating and enabled by its geometry. And then the one on the right is a light-absorbing paint, a light-absorbing material that has this microstructure here at the bottom. It's actually grown carbon nanotubes, but the really fascinating thing is that still the geometry is what makes this absorb 99.97% of all light. So that is really, I think, fascinating way to think about materials, such that we're not bound to, kind of traditional materials that we find in nature, like, wood has its own kind of properties, metal has its own kind of properties, and we kind of, can use those properties and build them into mechanisms. But we can actually not only design the mechanisms, we can design the material itself. So these types of structures are known as metamaterials, and there are many different types of metamaterials, some of which I've shown in the previous slide. So including electromagnetic metamaterials, they can be waveguides, they can bend light, such as optical metamaterials, acoustic metamaterials, and mechanical metamaterials. So mechanical metamaterials are kind of neat because we can kind of bring those together with the 3D printing and fabrication aspect, and design those geometries, and then use 3D printing technology or any type of fabrication technology to realize those in kind of like a physical artifact. So mechanical metamaterials are, one definition that I really like to use is that mechanical metamaterials are artificial structures with unusual properties that originate in their geometry rather than in the specific material that they're made of. And the key here is really that the underlying material that used to be the governing factor for mechanisms is not anymore, but really the geometry, the way that you arrange those little beams, that is what defines how the material will behave, what properties it would have. So yet another fascinating fact that drew me to this whole field is that metamaterials consist of many kind of little cells, unit cells that are arranged in a grid, and they only work properly if they work together. So what does that mean? Here's one example of an auxatic metamaterial. An auxatic metamaterial is kind of a structured material that has a negative Poisson's ratio, which simply means like if you compress it in one direction, it would also compress in the orthogonal direction, something that a normal material would not do. So this is how it looks like. So you see how it's being compressed vertically, and then it's been also pulled in horizontally. Regular materials would do the opposite. Regular materials would kind of, as you compress them, expand in the opposite direction. So what's interesting about this is that this works if you have multiple of these cells put together. If you isolate just one of the cell here, it doesn't have that property. It actually has a Poisson's ratio of 0. So you compress it downwards and there's no contraction on the orthogonal dimension. So that is something that I find really interesting, not only that we can engineer these properties, but we can also kind of embed different geometry, different functionality into these structures by arranging those in an interesting manner such that they work together to fulfill that function. So now the question arises, well, that is really intriguing. So if we can do these types of unusual material properties, can implement those, what else can we do? So we essentially set out to kind of extrapolate from this idea of being able to create structures, geometries that do kind of implement an unusual material property, and extrapolated from that and thought like, well, what if it's not only material properties? What if we can, embed way more functionality into the structures? What if we can embed functionalities that, can receive input, process that input to produce output? So essentially, I like to define that as kind of structures that embed functionality such that they can react to simple input with complex behavior. So in other words, you can think about creating passive structures, passive geometry that is printed, that where the material is the device. So it goes beyond just engineering the properties of the material, but really engineering a multitude of functionality that goes into those passive structures. So what could this look like? Here are a few examples. You can arrange these cells in a way that they implement mechanical or even robotic movements, such as this walker. We looked at structures that can also embed logic, so fully combinational logic, and make decisions within the material. We also looked how to change the outside of the material, essentially, to kind of communicate to the user, or change how the material interfaces with the world, like changes its kind of if you have a shoe, kind of like how slippery it is, and things like that. And another thing we were also interested in is, I talked a lot about, or I mentioned a lot, 3D printing these structures, but 3D printing is still pretty slow. Can we redesign them in a way to make them more mass fabricable? So for example, thinking about developable structures that can be laser cut, which is way faster. So I want to go through some of these a little bit. So I categorize those by their main functionality. So one is really, we can create materials that have specific actuation. So materials that are mechanisms that implement complex motions that go through their structure to kind of have like some complex output. Here's one example of a door ledge. So essentially the way that this door ledge works is that the cells are arranged, like it's really about the placement of those cells in order to make this material, happen to have the functionality of a door ledge. And essentially, the way that it works is that there's this underlying grid, and we can have this cell topology. So any of those edges are kind of fine. And the main components that we place are those rigid cells that only rotate with motion, so they transfer forces. And then we have shearing cells that have 1 degree of freedom, and they can redirect forces. And that really allows for a controlled directional movement in order to implement such mechanisms. Here are a few more examples. You can make pliers that are printed in one piece and strong enough to tighten screws or lift things. And then we also saw the walker in the very beginning, so which again, by arranging those cells properly such that they work together to implement that motion, you can use this material, this cell vocabulary essentially to implement these robotic functions. And obviously we want to enable users to create such mechanisms too. So we implemented this online tool where users can design the materials and test them out right in the browser. It's implemented in HTML and JavaScript. And the next step that we're looking at is essentially, so these devices that I showed were defined at design time. So you design the placement, you send it to the printer, and then they have the functionality that they have. However, what's also interesting thinking further is like, how can we implement multiple functionalities into one single material that we can switch through later after it was fabricated? So how can we create reconfigurable metamaterials? That's something that we just worked on, kind of creating active cells where the shearing angle can be actuated. And so those modules can be inserted after fabrication into the material in order to create more complex functionality. So here's just one early result that I wanted to show you. So we can place these rigid cells as before, and also compute the placement for these active cells and the control code of how to control those such that we can achieve that one target path, but we also looked at multiple paths that kind of where the rigid cells stay fixed, so the topology stays fixed. You don't have to reshuffle the cells around, but you can achieve multiple target paths by just changing kind of like the way that the actuated cells are driven. And that we implemented that into a inverse design tool. So essentially, the user defines the target paths, and then we look at finding the cell placement. So where do these rigid and active cells go, such that we minimize the error between the user-defined target path and what our material is achieving right now. Okay. So the other major thing that we're working on is kind of materials that can make decisions. So materials that can employ computation, combinational logic, such that you can, have a simple input and then they, decide what the complex output should be. Here's one quick example, which is a door lock. Users input the code, and then only if that code is correct, this blocker is pulled out such that the door latch is unblocked and people can open the door. So this is an example for this, digital metamaterials, as we like to think of those. We implemented signal transmission, routing, gates, amplifiers, and so on and so forth, kind of like common, signal processing elements. And also, I wanted to point out that we have gates, including the NAND gate, so making it full combinational logic. Now, the fascinating thing about this one is that these cells transmit signals. This is just a signal transmission line by a small displacement. But that also means that you can add like another kind of lever there, if you so will, and utilize that displacement as an actuator. So every cell can be an actuator at the same time. And so you can end up with kind of like reconfiguring kind of the analog part of the material in many places, like maybe thousands of cells, if we can get to small enough cells to create these materials that can reconfigure themselves into very different stages. So that is something that we're also working on right now, and I'm very excited about to build like a bigger framework where we understand these metamaterials on a different level. So I want to skip to the conclusion essentially, because we've seen some of these things in my preview. But essentially, what I want to get at is that we really have this unique opportunity to create materials that can do very complex things, receive input, process that input to create output and configure themselves, for example, so really the material can be the device. Main takeaways would be, one is we can embed functionality into passive structures to simplify the actuation. That's one big opportunity here. The second is there's lots of potential for reconfigurable metamaterials. So you can have multiple functionalities and you can choose from those later after it was fabricated. And third is that we can leverage the deformation of the structures to act as thousands of tiny actuators to reconfigure, for the material to reconfigure itself. And geometry is key for all of these challenges. It's a highly interdisciplinary field, between, my limited view, I would say like HCI, geometry and computer graphics, engineering really, and also design. So with that, I want to kind of conclude my talk here. If you're interested in any of these things, I'm always looking for, enthusiastic students and collaborators at all levels, also for the summer or for fall, whatever, whatever fits your schedule too. Reach out, let's chat, and thank you so much for having me.
Great. Thank you so much for the inspirational and extremely cool motivational talk, Alex. Now I would like to invite Yiyue Luo, who is a fourth-year PhD student in the Computational Design and Fabrication group at MIT Electrical Engineering and Computer Science, advised by Professor Wojciech Matusik and Professor Tomas Palacios. Before joining MIT, Yiyue received her Bachelor of Science in Material Science and Engineering at the University of Illinois Urbana-Champaign. Her research lies at the intersection of computational fabrication, wearable electronics, and machine learning. Yiyue, whenever you're ready.
Let me share my screen. Yeah, thank you for the introduction, and I'm very happy to present my work in the seminar today, and thank you for having me. And today I would like to talk about my work on digital fabrication of functional textiles. Textiles are everywhere in our daily life. So our daily wearings are made of textiles. Our homes and offices are filled with textiles, spanning from kitchen supplies, furniture to plush toys. And this can go beyond, and textiles are also widely used in healthcare, automotive industry, aerospace, and so on. So given the wide variety of everyday applications, textiles has been one of the most promising platforms for ubiquitous and seamless integration of technology in our daily environment. However, to integrate functionalities into textiles effectively for real-life applications, there are a few challenges. So first of all, textiles are generally soft, flexible, breathable, and provides comfort during natural human activities. So ideally, functionalities need to be integrated into textiles in a seamless manner, meaning that maintaining the softness and flexibility of the textiles. Also, the integration should be customizable and programmable, meaning users should be able to easily specify, edit, and even preview the integration of functionalities. And the integration should be ideally scalable as well, meaning that the functionality can not only be integrated into a small sample patch, but should be also able to integrate it into full-size garments like sweaters or even larger scale fabrics like furniture coverings or carpets. Also, given the long-established textile manufacturing market, it is also important to have the functionality integration process compatible with the current existed textile manufacturing methods for broader applications. And so digital machine knitting comes into the picture for all of these challenges. So digital machine knitting is one of the most popular textile manufacturing method in the textile industry. And given users specified low-level instructions, it generates fabrics by forming loop-over-loop structures automatically. It offers an addictive textile fabrication process in a computational manner. Here shows a more detailed overview of a V-bed webbed knitting machine. So there's a front and back bed of needles, and each needle is composed of a hook, which can catch the yarn and hold the topmost loop in the column, and a slider, which can be actuated to move vertically to assist in holding and transferring the loop. And during the knitting process, the yarn carrier feeds the yarn with proper tension and move along the bed while each needle moves up and down synchronously to perform the operations as we programmed. So here shows a set of digital machine knitted garments designed and fabricated by our lab mate Alex. As you can see, with advancements in various design algorithms, digital machine knitting can directly manufacture wearables with complex 2D shape and 3D geometry, such as a beanie, a sweater, and trousers over here. And the knitted fabric is soft, stretchable, and breathable. And with different combinations of the knitting operations, we are able to generate a diverse set of texturing and color works in the fabrics as well. And in the following of the talk, I would like to show 3 different projects which integrate functionalities into textiles using digital machine knitting for different applications. So first, I would like to talk about fabricating tactile sensing wearables for learning human environment interactions. Humans are particularly receptive to tactile cues throughout the body, including hands, limbs, and torso. And leveraging such rich and constant tactile feedback, we are able to extract information from the external environment, control and adjust the contact force and poses, and therefore to perform diverse set of daily activities. The recordings and analysis of full-body human-environment interaction is important in diverse fields, including healthcare, sports training, and human-robot collaboration. However, it remains challenging as this would require large-scale wearable sensors with low cost, dense coverage, conformal fit, and minimal presence to human being when during data collection, when humans are performing daily activities. So here we present a scalable manufacturing of full-body, high-density sensing garments by seamlessly integrating functional fibers using digital machine knitting. So the design garments are soft, stretchable like regular clothes with complex 3D conformal geometries. And we further develop some machine learning-based computational workflow to assist in the sensing array calibration, as well as the recording and analysis of the full-body human environment interactions. So our textiles are based on coaxial piezoresistive fibers, which was created by coating the stainless steel thread with a piezoresistive mixture, which is made of the mixture of PDMS, graphite, and copper nanoparticles using a customized setup. When a pair of fibers are orthogonally overlapped, sensing units locates at the intersection points, and where a piezoresistive layer was actually sandwiched by two conductive electrodes. With the increasing applied normal force, the resistance of the sensing unit drops and therefore converts the pressure stimulus into electrical signal. We then use a digital knitting machine to automatically integrate the functional fibers into the textiles with our designed shape and geometry. The generated knitted fabric with integrated functional fiber is soft, flexible, and stretchable. And by generating and overlapping two pieces of fabric, one with horizontally integrated piezoresistive fiber and one with vertically integrated piezoresistive fiber, we can embed the pressure sensing matrix into fabrics and garments. So more specifically, we fabricated a full-size sensing vest, a pair of sensing socks, gloves, and a conformal robot arm sleeve. And using our full body sensing garments, we are able to collect millions of frames of tactile data set featuring diverse human environment interactions. And this includes grasping different objects, doing different body movement, and other activities. And we demonstrate the capability and the utility of our platform by leveraging our data for the environment and action classification, motion pattern discovery, and full body motion human pose prediction. Here shows an example. Our tactile sensing vest has over 1,000 sensors with a discriminative resolution of 2 centimeters. The full-size sensing vest shows the force distribution during a wearer is performing different actions like sitting, standing, leaning to the wall, or something like that. And the real-time pressure imprints indicate the wearer's pose, activity, and even the texture of the contacted surfaces. We then capture a data set where a wearer performs different poses, and then we project a high-dimensional sensory response into a 2D space. We then observe that the recordings from different classes of poses naturally form very distinctive clusters, indicating the discriminative power of our sensing vest. And as another example, we can record a person's footprint with our tactile sensing socks. So humans maintain the dynamic balance of the body by redirecting the center of mass and exerting forces on the ground, and which results in distinct force distributions on the feet. And given this, we actually demonstrate that a person's pose can be estimated from a change of force distribution over time obtained by our tactile socks. Basically, we record synchronized tactile data from a pair of sensing socks and a full body motion capturing system, while the users are performing different diverse actions. We then train a model to take in a sequence of tactile inputs from both of the socks and then outputs the joint angles spanning over the legs, torso, and arms, representing a person's body pose. And here is some qualitative results of our pose estimation by taking the tactile responses from a pair of tactile sensing socks and then outputting the person's body pose. The model learns to make predictions that are both smooth and consistent over time, while a person is doing a diverse set of daily exercises. And finally, we also demonstrate that our sensing array can be used as a tactile robot skin. So most of modern robots rely only on vision. However, large-scale and real-time tactile feedback is critical for dexterous robot manipulation and interaction skills, especially when vision is occluded or disabled. So our functional textiles enable conformal coverage of the robot arm, gripper, limbs, or some other functional parts with complex 3D geometries. And here we show a sleeve for KUKA robot arm, and our platform offers the robots with real-time tactile feedback for unobtrusive multi-point collision detection and physical human-robot interactions. Then going back to the Tactile line so far, we've seen textiles with integrated customized functional fibers. And then I would like to dive into fabricating textiles based interactive user interface using off-the-shelf yarns and delicate machine knitting techniques. So here we showed the textile-based interactive educational patches. It contains two parts, a bottom knitted pad with conductive traces for the ease of electrical connection, and the top interchangeable knits with integrated pressure sensor and customized graphical designs. And here shows another examples where the bottom electrical traces are incorporated into a full-size glove. And different top sensing layers with customized graphical designs can be coupled with the same electrical traces to form a wearable user interface for different using scenarios. So our integrated pressure sensor builds on double-layered knitting structure. We enable the sensing capability by inserting off-the-shelf conductive yarns at specific locations on both the top and bottom layers separately. We leverage jacquard knitting to form the interlocked double-layered base structure and use plating to embed graphical designs in front of the sensing unit with various yarns with different colors or different textures. And we also use short rolls to create local curvatures with conductive yarns for larger contact area. At the rest state, without any external applied pressure, large resistance is obtained because the knitted conductive yarn loops interlock very loosely. But when applying a load, the top and bottom layers collapse and the interactions among the conductive yarn loops increases, and therefore creating more electrically conductive path and significantly reduce the resistance. We offer an interactive design interface for users to customize sensors, color, sizes, position, shapes, and even performance with a bunch of handy tools. Our interface can further convert designs into low-level knitting machine instructions, and then allowing users to fabricate the devices with an industrial digital knitting machine automatically. So the resulting knitted structure enables minimal manual post-processing and assembly and allow removable electrical connections. And as I briefly mentioned earlier, the sensing units can also be integrated into wearable garments as a wearable user interface. Here we show the numpad wrist wrap and also a music controller glove. So as a summary here, we present an interactive and sensing textiles leveraging off-the-shelf yarns and delicate digital machine knitting techniques. We generate soft, deformable, portable sensing units and coupled electrical connections. So our prototype requires minimal manual post-processing and can be easily customized and integrated into any existing knitting garments design for diverse using scenarios. And lastly, we demonstrate the integration of actuating capability into textiles by leveraging intrinsic textiles property. So pneumatic actuators have shown enormous promise in applications such as soft robotics, assistive wearables, and interactive devices due to their low response time and relatively large output power density. Over the last decades, researchers demonstrated diverse soft silicon-based pneumatic actuators designs by molding, which is one of the most common technique for pneumatic actuators manufacturing. And recently, textiles and fabrics have been devoted as candidates for soft actuators, thanks to their ubiquitous utilization in everyday life, high strength to weight ratio, and compliance with the human body. Researchers have demonstrated textile-based pneumatic actuators through intrinsic modification or extrinsic reinforcement of the textiles. These strategies However, while effective and now in widespread use, are both manual and require trial and error cycles to optimize designs. Further, incorporating sensorization into such workflows is rarely considered, and simple established recipes for doing so are lacking. So to overcome such shortcomings of the current workflows, we proposed a method for rapidly fabricating machine-knitted customizable pneumatic actuators with integrated sensing. And we also offer a predictive simulation and interactive graphical user interface for users to design and preview the actuator behaviors easily. So here shows an overview of our typical machine-knitted sensorized actuator with one actuation region, 3 resistive pressure sensors, and 2 swept frequency capacitive sensors. So our actuator is composed of 2 parts: an off-the-shelf thin wall silicone tube, which serves as the base of pneumatic channel, and a knitted sheet with programmed stitches, which will be wrapped over the silicone tube and confines the shape of the inflated actuators. The deformation of the actuator is mainly defined by the knitted sheet with locally variable extensibility. So we manipulate the extensibility of the knits by integrating some elastic yarns at the back of the tubes over here. As an example, in the tube over here, the front of the tubular knits is constructed with normal knits with normal acrylic knitting yarns, and the back we have it's integrated with some elastic yarns shown in the curved box over here. The elastic yarns, it's about 100 times more extensible than the normal acrylic yarns. So we then wrap the knitted sheath over the silicone tube and anchor both ends of the wrap tube by clamps. And when the silicone tube is inflated, the elastic stitches at the back side of the tube tends to extend more than the non-elastic stitches at the front. And this will force the silicone tube to bend forward. We also leverage some plating techniques to insert conductive yarns at specific locations where the conductive yarns are blended with normal acrylic knitting yarns. The knitted conductive yarns interlock loosely when there is no external pressure, and when applying a load, the conductive loops collapse, resulting in more electrical path, and therefore the resistance drop. So it's also worth mentioning that we actually apply a few knitting tricks to prevent the pressure sensors from being stretched when the actuators inflate and ensures the reliability of the pressure sensor performance. We also integrate capacitive sensors. So swept frequency capacitive sensing leverage the fact that the alternating current signal of different frequencies flow through different paths at the capacitive interface between the electrode and the body contacted objects. So here we integrate conductive yarns at specific locations on the knitted actuators as the capacitive sensing electrode. And by collecting amplitude responses over a range of frequencies, we retrieve information on the existence of human touch or human contacted objects. And to allow users to design and preview the inflated actuators quickly, we provide an interactive design system and a predictive model by which users are free to specify the actuation region and the sensor locations. Users can also preview the actuator's shape in real time and export low-level knitting machine instructions of their ideal design, and then it can go for immediate fabrication using our digital knitting machine. So we incorporate a predictive simulation model in our user interface, which allow users to preview the inflated shape of the designed actuator. And thanks to our data-driven strategy, where we capture the shape of individual normal and elastic stitch faces of the fabricated actuator under pressure, we can actually obtain a realistic simulation result. And here shows some qualitative results of our predictive simulation on the J and S shape actuators. We further conduct a user study to evaluate the usability and effectiveness of our computational design interface. During the study, we asked the participants to perform two tasks without and with the simulation feedback. The first task asks users to design an actuator such that the endpoint of the actuator would make contact with the specified location when inflated. And the second task asks users to design an actuator that can circumnavigate a specified obstacle when hitting target when inflated. And here are some simulated and fabricated examples designs from users. And in general, participants achieved higher accuracy in both tasks and considered the task easier and obtained more confidence in their design with our predictive simulation tool. And such results reiterate the usability and effectiveness of our design pipeline. And finally, we demonstrate diverse application scenarios of our machine-knitted pneumatic actuators. So our actuators have outsized potential as assistive variables because they are low-cost, lightweight, breathable, conformal to human body, and compatible with the current garment manufacturing process. So here we seamlessly integrate our actuators into knitted garments such as a glove and sleeve, and they are fabricated in one machine run as a whole piece of garments. Minimal muscle activities are observed while completing tasks and motions when using the assistive glove and assistive sleeve. We also design and fabricate soft hands with 6 individuals, machine-knitted actuators, and by activating different sets of actuators, we can perform diverse grasp on different objects of various sizes, geometries, weights, from a tennis ball to a wooden block in a quite reliable manner. And here we demonstrate a 2-finger gripper with integrated pressure sensors and sweat frequency capacitive sensing. The amplitude response from the sweat frequency capacitive sensing offers real-time feedback on the presence of object along the finger interior, while the integrated pressure sensors provide real-time feedback on the quality of the grasp. And our machine-knitted actuators with integrated capacitive sensing can also be used as an interactive robot. So we assemble 4 separate actuators with each integrated with an electrode for the sweat frequency capacitive sensing. The real-time sensing feedback allows the robot to respond interactively when a human's touch is detected, and they either activates or deactivates. And lastly, we demonstrate our actuators can be arranged as legs for a soft quadrupedal robot. So each of the 4 legs here consists of 3 actuators, 2 of which bend forward and backward, and while the third one bends the leg upward vertically. So we predefined the motion pattern of each leg. So the predefined motion pattern actually form a rowing-like motion, and then pushing the quadrupedal robot forward, backward, or even doing a turning motion. So, as a summary here, we demonstrate how functionalities can be integrated into textiles using digital machine knitting by different means and for different applications. More specifically, we showed full body scale tactile sensing variables by integrating customized piezoresistive fibers, and then showing interactive user interface by leveraging off-the-shelf yarns and delicate machine knitting techniques, and as well as pneumatic actuators with integrated sensing by leveraging the intrinsic textiles properties. And going forward, we are very excited about the general direction of sensing and control using textiles. For example, integrating multimodal sensing capability into textiles for seamless and real-time monitoring, fabricating novel textile-based tangible user interface for everyday usage. And on the other hand, despite sensing capabilities, we would like to explore output and actuation capabilities for applications such as exoskeletons, haptic devices, and so on. So we envision that our regular daily wearings will in the future serve as an input and sensing platform as well as an assistive or augmented output devices. And with that, I would like to thank my collaborators in all the papers I mentioned in this talk, and I'm open to any questions.
Great. Thank you so much, Yiyue. That was an amazing talk. Very, very exciting ideas and applications, I think. And just great because both talks, I feel like, presented this vision that's almost like science fiction. Like the things that we can create have so much embedded functionality. So now I would like to invite everyone to post their questions in the chat, and we'll have like a short Q&A session. I guess while people are typing, I could ask a few questions. So Yiyue, I know you mentioned like in the last slide that one of the things that you're interested in doing is maybe looking forward to creating things with haptic feedback. And have you at all thought about like what's the road to getting there? I know that some people have been working on like spacer fabric type materials and knitting. What do you think like would be the path there?
Well, I think for haptic feedbacks, there are actually a bunch of options. But when it goes to textile specifically, I think the options will be narrowed down a little bit. So something I think that's promising would be use electromagnet effects. For example, we can easily embroider some coil on the fabrics and then putting some magnetic materials on top of the textiles and then generating doing some actuation with inputting some kind of AC currents into the coils. And some other would be using intrinsic textile properties, like you mentioned, generating some kind of spacer fabrics using the structure of textiles itself. Those are good options as well. Yeah.
Great. Yeah, that's really cool. Adriana asks, she says, this is really great work. Is there a limit on the resolution that you can get on sensing and or actuation?
That's for me, right?
Yeah.
Yeah.
Sure.
So, well, I guess yes, there should be some resolution limitation in terms of the fabrication process. For example, when we are doing knitting, so it's a resolution limits on each of the cores of knitting yarns. Those would be the most obvious resolution limitations in terms of integrating functional fibers and so on. And also when it gets to textiles, it's actually really hard to when it gets to digital manufacturing, it's kind of hard to manually control the very fine resolution like we are making sensors by hand. So I imagine that I also really experienced as well. It's actually very hard to do very fine resolution like what the current state of the art microelectronic devices can do. But I think the good thing about integrating functionalities into textiles is you can easily scale it up with larger with coarser resolution, but with larger area. So I think that's the advantage of using textile for it.
Yeah, very exciting. Yushan asks, this is very cool. Could you talk a bit more about how the data-driven simulation is achieved for the actuated tubes and whether there's any difference between elastic yarn and acrylic yarn?
Yeah, sure. So without sharing the slides, I can just talk about it. So the elastic yarns, it's, as I mentioned, it's much more extensible than the normal acrylic yarns. So it's actually more than 100 times more extensible than the normal acrylic yarns. And how we do the data-driven strategy is like, so we first fabricate an actuator with only the stitches of normal acrylic yarns, and then fabricate another one with only elastic stitches. And then we inflate pressure into both actuators, and then we use a camera to capture the shape of both actuators, and then measure the height and width of each of the stitch faces. And then we'll incorporate this information into our physical simulation to generate the realistic results we have here.
Very cool. Yes, thank you for answering that. Blenderhead asks, for wearable applications, do the pneumatic actuators need to be fed by pumps with electrical controllers? Have those been miniaturized sufficiently for such settings?
Yeah, that's a really good question. Yes, pumps need to be like, of course, it's essential for pneumatic actuators. But for this project, we actually have an external pneumatic system. We haven't miniaturized it in this project, but I think out in the market there are actually a lot of miniaturized pump system that can fulfill the requirement of wearable pneumatic actuators.
Okay, great. Uh, People, please feel free to ask more questions. I also wanted to ask, so earlier when you were talking about haptics, you said you might be possible to embroider like certain types of coils into the fabric. So I was just wondering, why would you choose, like, have you explored kind of the extent of how fabrication specific details of the textiles can affect the functional design? Like why choose embroidery over knitting or knitting over embroidery? And sort of like, are there aspects of knitting that you could use to create different circuits or circuits with different properties?
I see. Yeah, so well, that's actually a very good question. So I think both digital machine knitting and digital embroidery are fall in the category of like computational design and digital fabrication. So the only difference of knitting and embroidery is like so they have a few main differences. Like they generate fabrics in very different way. So in knitting machine, they generate fabrics by forming a loop over loop structure. So in the knitting machine, it actually has to be fabricated course by course, basically row by row of yarns sequentially. But in the embroidery machine, you basically have a top yarn and a bottom yarn, and you are actually feel free to embroider at each arbitrary positions in a flat fabric. But I think the main advantage of knitting machine is it's available to generate arbitrary 2D, like arbitrary 3D geometries by performing some either decrease or increase of the needle operations. So they both have pros and cons. So I think it depends on integrating different functionalities and integrated into different ways, different layouts and so on. I think people like researchers need to think about what is the best way to do it, because sometimes it's super hard to incorporate using knitting machine, but it's relatively easy using the embroidery machine, and vice versa. So I think that's something researchers will have to think about.
Yeah, that's very insightful. Thank you. Milan asks, it seems that there's a bit of latency for the garment user interface. What are some factors that can contribute to this, and can we improve it for real-time applications?
I, uh, I'm a little bit confused about the question, like which interface we're talking about, or
So it just says garment user interface. So I'm not sure if that refers to the knit UI work, or if that refers to the actuated sensing work, or if that refers to the first one. Maybe Milan can clarify, and then we can continue the question.
okay.
Great. I guess I also wanted to ask Alexandra something. So I was very like, is super cool the extent of the types of applications that you can create using like these metamaterials, especially like the digital kind of like digital applications. And I was just wondering, it seems that designing these kinds of structures are not very intuitive because they're so novel. What do you think we still need to make designers kind of like literate in this kind of design? Is that something that we're interested in doing? Like, what do you think we like still needs to happen?
Yeah, I think there are two things. I think we need design tools that are, both forward design tools and also inverse design tools. So the forward design tools are the ones that can foster exploration. So where, people can design things freely and then, come up with new things that we might not have thought about. And as we understand more of those maybe novel structures, we can take those insights and feed them into inverse design tools where they become the objective. So I think for known things, and you've seen maybe in the talk that we do both. So for things where we say like, well, we know we want to have robotic motion, and here are kind of the movements that should happen, an inverse design tool makes most sense because it's really not intuitive how to place those cells at all, because they constrain each other and have like more complex relationships to each other essentially than is maybe apparent by just glancing at it. And then again, kind of like the exploratory tools, would serve the purpose of giving us new objectives to optimize for and kind of like understanding the field a little bit more. So, that could also include things like maybe games, gamification of such exploration tools. It doesn't have to be design new material, but maybe it's like, packed into something else, and it gives us kind of like new topological structures that we can, understand better and integrate it in other tools.
Yeah, that's a very fun idea. I can imagine that there's a lot of these types of structures that nobody has found yet and that kind of still are out there waiting to be discovered. So that's a very fun idea. I like that. You're back to the original question. I think Milan was talking about the user interface when you like press on the button. So in Knit UI, like if you were to hit the button, they commented, it seems like there's a bit of latency. It takes a second when you press on the button on the hand compared to when the result then showed on the screen. So I think they asked, can you comment on like what are some of the factors that contribute to the latency and how can you improve it so that maybe, I guess if you're like playing a game, you want to be able to hit it as, you want to be able to get the response very quickly.
Yeah, I think the latency right now is mostly because of the post-processing of data we did on trying to minimize the false positive response from pressing the button. But I think going like forward, if we want to improve the latency, most of them would go for like a sensing circuit with higher frame rate, and then with like more optimized post-processing to try to minimize the false detection thing. Yeah.
Very cool. And is that because the circuit, like conductive yarns, are very close together, so it's easy to kind of have them actuate when they may not actually be pressing down on them?
Yes. So how I do the post-processing is like I need to make sure there's a short period of time with like enough response, with enough electrical response from the sensor. Then I treat it as a positive input.
Yeah.
So I think something over there definitely can be optimized.
Great, very cool. So please, if anyone has any like last questions, you can ask them. Otherwise, we will conclude the session and we invite everyone to join us for like a post-talk discussion in the Zoom. Please, if you are going to be joining the Zoom and you don't have, like if you're going to be joining the Zoom, please indicate in your name that when you join that you're from the Computational Fabrication seminar. So I'll post a little bit of instruction on how to do that. And then, yeah, please do that so that we can make sure, you're people who are actually supposed to be joining the seminar and not just people like, I'm looking for Zoom links to join. So I'll be posting the details for that. Thank you again to both speakers for such amazing talks. We all really enjoyed them. And it was a very cool glimpse into the kind of novel work that people are doing in this kind of functionality that is inherent to the fabricated object. So thank you again. I'm sure everyone is clapping at home. Lots of clap emojis on the chat. And yes, please join us on Zoom. So I'll be ending the live stream as soon as I post the Zoom link. So thank you again. And